The title of this notes is Rational Functions Wholes. So our goal is to be able to analyze the wholes of a rational function. So same way we started with vertical asymptotes, you're going to completely factor the numerator and denominator, and you still do not want to simplify. If you have a factor that occurs in both the numerator and denominator, then you have a whole. So remember, when we're factoring, we cannot just cross things out if there's addition and multiplication. You cannot do this because there's a plus sign. So to factor, here we have an example. Same example we saw last time. So two factors that multiply to -6 and add to be +1. So it's going to be x plus 3 and x minus 2. They have to have different signs because their product is negative. And in the denominator, two factors that multiply to -2 and add to -1. So -2 and +1. So here's a factor that occurs in both the numerator and the denominator. That means that that factor shows the location of a whole. What value would cause that factor to be 0? It's +2. Or you can just say, hey, flip the sign, +2. So we now know that there's a whole when x equals 2. Notice last time we talked about there's a vertical asymptote. So we also know there's a vertical asymptote at x equals -1. But at x equals 2, there's a whole. What happens if you see a factor multiple times? If the factor, after you cancel it out, is left over in the denominator, it's going to be a vertical asymptote. If it's not left over in the denominator, it's going to be a whole. So an example of that, let's say you factor, and all your factors are like this. That's all you have. So this would cancel out. Nothing's left behind, so it would be a whole. What if you had something like this? All the factors are the same. It cancels out. I'm thinking it's a whole. It cancels out. I'm still thinking it's a whole. But look at that. It's left over in the denominator, so it's actually going to be a vertical asymptote. If the factor gets left over in the denominator at all, it's going to be a vertical asymptote. It has to cancel out of the denominator to be a whole. So that's where we find the x-coordinate of a whole. So now we're going to talk about how to find the y-coordinate of a whole. A whole is also called removable discontinuity. Discontinuity because you're not defined there. It's a gap in the function. But it's called removable because you can actually remove the factor and the problem doesn't change. So your steps to finding your y-coordinates, you're going to remove any factors that appear in both the numerator and denominator. And then secondly, you're going to substitute the x value of the whole, that's what we just practiced finding, into the simplified factored form of the equation. So let's look at a couple examples of that. So first we want to factor this. And I'm actually going to change this problem so that we have a whole, so that this makes sense. So let's change the top to say -1. That way we can talk about the whole. So there is a factor that cancels out in both the numerator and denominator. And that tells me that there's a whole at x equals 1. What is the y-coordinate of the whole? So to figure that out, I would think about, well, what's left behind? Nothing's left behind in the numerator, so I'm just going to put a placeholder 1. And then the denominator is x plus 4. If we substitute 1 into this simplified function, we get 1/5. So that tells me that the whole is located at 1/5. So that's where there's going to be a gap in that graph. If I was graphing it, and I haven't analyzed what the rest of the graph looks like, but that's 1/5, that's 1. So the graph might be doing this. There might be an asymptote. I would have to do a total analysis to figure that out. All right, let's look at one more example. So this time the example is x squared minus 1. And again, the same denominator. So I would recommend pausing the video here and trying this one on your own, and then I'm going to put the answer up. This is the end of our notes.